Electric charge and field summary. Electric charge in a closed system is conserved. Closed system means you isolate a certain part of space and you don't let anything come in or out. Comes in two flavors, positive and negative. You can charge objects by induction, where the objects do not touch, and the charged object, if grounded, will have an opposite charge to the charging object. It picks up or sends down electrons to the ground. And of course, on any of this summary, you can go back to the notebook presentation on this topic and find more details. And then the key part there is removing the ground before the charging object gets removed. Conduction, the objects touch, they contact each other. Okay, so a good way to remember it, conduction, contact. The charged object picks up a like charge from the charging object. The smallest free charge that exists in nature is the charge on the electron. 1.602 times 10 to the minus 19th coulombs, and typically for problems we just use the 1.6, and all larger charges have to be an integral multiple of this number. Coulomb's law quantifies the force between two charges, and when in vector form it also shows you the direction. And the force is 1 over 4 pi epsilon 0 times Q1, Q2 over R12, where R12 is the distance between charges 1 and 2. Don't read it as R12. And R hat is a unit vector, which is on the line connecting Q1 to Q2 with a magnitude of 1. Another way to write 1 over 4 pi epsilon 0 is by saying it's K, the Coulomb's constant, and epsilon 0 is 8.854 times 10 to the minus 12th, and Coulomb's constant, K, is going to be 9 times 10 to the 9th. Okay, 9 times 10 to the 9th. The electric field, due to a point charge, is a property of the space about the charge. It's also known as a vector field, and it is derived from Coulomb's law. So we start right here with Coulomb's law, and then we want to find the field due to a large charge, capital Q, where Q is a small positive test charge placed nearby. And we do that so the electric field from the little q doesn't affect anything, it is so small. So we just rewrite Coulomb's law like that. Then we will divide through by this little charge, little q, and we come up with the equation for the electric field. When you know the field, you can find the magnitude and direction of the force on any charge that enters that field. And another handy relationship is right this, F is equal to QE. We don't always deal with a single charge or a couple charge. Frankly, we normally deal with continuous charge distributions where you have shapes, right? You have various, like you want to find the electric field due to a sphere or to a rod. And that's very difficult to calculate because that's a vector sum. Right? You got to find the electric field, for example, at this point due to every single piece on this charge distribution. However, if you have very good symmetry, you can calculate it with a pretty straightforward integration. And basically what you're doing, you're finding the total electric field by adding up the electric field due to every little point, every little tiny point charge. And again, that's just KQ over R squared. And we're going to do it, or it was done in the presentation, for a uniformly charged rod, a semicircle of charge, a ring of charge, and a disk of charge. In addition to having a high degree of symmetry so the integration is easy, the charge Q must be distributed uniformly, so every little piece of charge you take, every little dq, has the same charge on it. And there are three very key definitions that we'll be using. We have a linear charge density, lambda is equal to the total charge over the length, surface charge, total charge over area, and volume charge, total charge over volume. And since we'll be working with little pieces of Q, dq, we just take the differential of all these pieces, and we come up with these handy relationships. And again, lambda, sigma, and rho are just numbers, so they don't have a differential, it's just the number. In the notebook presentation, all of these symmetries were calculated. For here, we're just going to present the picture of what it looks like and what the electric field is. So in the first one, the uniformly charged rod, that's the shape here, we wanted the electric field at the origin. And this is what it turns out to be. That's its magnitude, and the direction is in the negative x. We're assuming a positively charged distribution there. For a semicircle, which is related here, we want the electric field at this point, and we come up with 2k lambda over r, and that is in the negative y direction at point 0. Uniform ring of charge. This is just, well, exactly what it says, a ring. So picture a wedding ring, something like that. It's just a loop here, and it is centered on the x-axis. So if you want to visualize that, that's like a silver dollar stuck into the page of your paper. Half of it's through the paper, the other half is facing you. You want to find the electric field at point P. There will be no y component. The y components cancel out, and you're just left with an electric field in the x direction. And the only thing to be careful about here is, in this case, x is fixed. Most of the time you look at x as a variable, but it's the distance between the center of the ring to where you want to find the electric field. We then calculated the electric field for a disk of charge. This here is a silver dollar. Okay, it's a solid disk. And the way we did the integration there, we built it up with an infinite amount of thin rings, thin loops. And you came up with an electric field like this. And again, at point P, there is no y component. It is all in the positive x direction, assuming we had a positively charged disk. The last chapter that was dealt with was the electric dipole, which is a positive charge right here, negative charge separated by a distance, and we wanted to find the electric field at this point on the perpendicular bisector of the dipole axis. We find it's to the right, and this was the electric field that we calculated. We also calculated the potential energy of an electric dipole in a uniform external field, external electric field, and that is negative P, which is the electric dipole moment, dot the electric field. When you place a dipole in an external electric field, you can create a torque. We have our external electric field here in blue, and you can see how the dipole is arranged. And we're about to also review the electric dipole moment. That's P right over here. And that's equal to the charge times the distance between them. The electric field is going to exert a force on the positive side like that, negative side like that. What is that going to do? That's going to provide a torque. It will rotate the dipole. The magnitude of the total torque is QED sine theta. We then can replace QD with P. That's a term we define, the electric dipole moment. So the magnitude of the torque is now this expression. And what do you do if you want to turn that into a vector? Well, there you go. It's P cross E. And the electric dipole moment points along the dipole axis from the negative to the positive charge. This is a wonderful chart to understand electricity. There are going to be 4 key relationships when we study electrostatics. That's when charges are not moving. We're going to cover the top row of this chart in this unit, and the bottom row down here, we'll do that later in the electric potential unit, but I just want to show you the chart now. We start with Coulomb's law, and then we define the electric field from Coulomb's law. So we move to the right on the top row here. Now, both of those are vectors. So you can see we've highlighted it right there. Electric force and electric field are vectors. And moving from left to right, we kind of colloquially say you lose a Q. It just helps you remember what it is. So here you can see we had 2 charges. Here there's only 1. When we get to potential, moving down, we have potential energy and electric potential, and a nicer name for that is voltage. Those are scalars. And as you go down the columns, you quote-unquote lose an R. So from force to potential energy, you can see how this is just R. The force was R squared. Electric field compared to electric potential, again, you lose an R. Okay, so maybe that's not the most elegant way of showing it, but it's a nice, easy way, well, somewhat easy way to keep electric force, electric field, electric potential energy, and electric potential or voltage clear in your head.